Hi, Google has highly provisioned low latency network. It's the same network that powers products like Gmail, Google Search, and YouTube. So the traffic stays on Google's private backbone for most of its journey, ensuring exceptional user experience and high performance. Google's networking is very unique and it's a distinctive feature amongst all cloud providers. As part of networking on Google, let's look at some of the core concepts. Virtual private cloud, which is a virtual network topology for Google services. Load balancing, it's a service for distributing traffic across applications and regions. Now, before we look at networking, we need to understand IP addressing and CIDR blocks. Now, every location or device on a network must be addressable, which is very important. In the TCP/IP model of network layering, it's referred as IP address. IP addresses allow network resources to be reached through a network interface. So that's why it's very important for it to be addressable so that it can be reached. Each IP address must be unique on its network. Network address translation allows the addresses to be rewritten when packets traverse network borders to allow them to continue to their correct destination. Now, as part of IP addresses, there's IPv4 and IPv6. IPv4 is the fourth generation. It has 4 octets and it's a 32-bit address. Each 8-bit segment is divided by a period and typically expressed as a number between 0 to 255. Example 192.168.20.10. Now, typically IPv4 starts with 172, 192, 127 or 10 dot something. That's called class. Like class A, class B, class C, class D, class E, etc. Different classes are reserved for different boundaries. Now, when you look at IPv6, and one of the main reason IPv6 is being used now is because IPv4 is pretty much exhausted in terms of available IP addresses because of upsurge in IoT devices and lots of devices being connected to the network. IPv6 provides 16-bit blocks and it has a 128-bit address. There's 8 segments of 4 hexadecimal digits. Double colon is used for leading zeros. So in this particular example, all of these are zeros. So you can see there's a double colon that is provided so that it's shorter if a lot of IPs are not being used. Now, each address space is divided into a network portion and a host portion. The process of dividing a network into smaller network section is called subnetting. For instance, for this particular address, the first 3 octets are used to describe the network. So if I look at these 3 octets, they define the network. And then the last one is basically it describes the host. Now, the next part which we need to understand is the CIDR block, which is a classless inter-domain routing. And every time you will spin up any machine, then you will have to have some sort of network layer above it created before that. Now, think of a scenario that every IP is unique, and if you don't reserve enough space for subsequent IPs to be allocated for a series of servers. Now that becomes a problem. So that's where CIDR blocks come into picture. CIDR notation of 192.168.0.15.24 means that the first 24 bits of the IP address given are considered significant for the network routing. So basically the idea is that you can add a specification in the IP address itself as to the number of significant bits that make up the routing or networking portion. CIDR, it allows more control over addressing continuous block of IP addresses. So you will see later on is that every time we are defining subnet, it's basically this /24 or /23/23, depending upon how many consecutive IPs you need to reserve for your network. So with that, let's get a view of the Google's network footprint. Google Cloud's locations from redundant cloud regions to high bandwidth connectivity via subsea cables underpin the exceptional networking landscape. Google's data centers around the world are interconnected by Google Network, which by some publicly available estimates carries as much as 40% of the world's internet traffic every day. It's designed to provide the highest possible throughput and the lowest possible latency for applications. The network interconnects with the public network and more than 90 internet exchanges and more than 100 points of presence worldwide. So apart from the undersea cables, the point of presence, the main interest, as a GCP user is basically the number of regions, which is it's basically a geographic location. So for this example, you can see this is in Australia, it's in Sydney and Melbourne. So these are two different regions. US has multiple: US West, US Central, US East. Similarly, there are a lot of regions in Europe, India, in Asia Pacific. And then there's this zones concept, which is it's a deployment area within a region. So within a region, because of high availability and catastrophic reasons, if one location goes down, there are typically 3 different locations within a region where these the physical data centers live. Now, as you can see, as of today, there are 27 cloud regions, almost 82 zones, and there's a lot more coming. And this space keeps changing. Recently, there was one region launched in India, as well as one Melbourne was recently launched. So keep looking out for this space. There's always new regions, and zones get added. Now with that, let's try to get into the core concepts of Google networking. Now, projects which are a trust boundary of a scope can contain multiple VPC network. What is a VPC network? It's a virtual version of a physical network. It's implemented inside of Google's production network using Andromeda. VPC networks, including their associated routes and firewall rules, are global resources. So you can create a virtual network which spans across multiple regions and across the globe. So that's a very distinctive feature of Google. They are not associated with any particular region or zone. A VPC network provides the following: It provides connectivity for your compute engine, virtual machine instances, including Google Kubernetes Engine, App Engine Flexible Environment, and other Google products which are built around Google Compute or Compute Engine VMs. VPCs offer native internal TCP UDP load balancing and proxy systems for internal HTTPS load balancing. They connect to on-premises network using tunnels and direct connect options. They distribute traffic from Google Cloud external load balancer to the backends. Now, to set up any virtual private network, you basically have to select a region, and then you within that region you have to select zones. Now, as Google VPCs are global resources, it can span across multiple regions. So in this example, you have region A, which is US West 1, region B, which is US East 1, and there are 3 zones, and then there are 2 zones as part of region B. Then the concept of subnets. So each VPC network consists of one or more useful IP range partitions called subnets. So virtual private network, you have defined the virtual version of a physical network. So virtualized network. Now within that network, you divide the IPs into certain partitions, and that's basically is a subnet. Each subnet is associated within a region. VPC networks do not have any IP address ranges associated with them. IP ranges are defined only for the subnets. So it's very important to understand how all of these come together. A network must have at least one subnet before you can use it. And subnets are regional resources. So what that means is that subnet sits within the region. Now, each subnet defines a range of IP addresses. So when you create VPC network, Google Cloud offers 2 types of VPC networks, which is auto mode VPC network and the custom mode VPC network. Now, when you create a VPC, basically it's created with the auto mode network. So you will have one subnet for each region automatically created with it. In custom mode, no subnets are automatically created, and you get the option to actually create and specify your IP ranges. What's important to understand is that you can switch a VPC network from auto mode to custom mode, and it's a one-way conversion. Custom mode VPC networks cannot be changed to auto mode VPC networks. And each primary or secondary IP ranges for all subnets in a VPC network must be a unique, valid CIDR block. So the range in terms of the network portion and the host portion should not overlap. VPC networks itself, they only support IPv4 unicast traffic. They do not support broadcasting or multicasting or IPv6 traffic within the network. VMs in the VPC network can only send to IPv4 destination and only receive traffic from IPv4 sources. So with that, we have created these subnets, which is, again, regional resources. You can, subnets can span across multiple zones. Then comes your compute engine. Is basically where you do all your work. Now, they are spun up within that subnet range. So when we talked about CIDR block, so this is the network portion, and this is the host portion, and the host portion has, you can go up to slash 24. So those many IP addresses you can generate. The next is, once you have created all of these, you need a way to restrict incoming, which is ingress, as well as outgoing egress traffic into the network. So you should be able to define if this particular machine can talk to this machine. So that's taken care by routes and firewall rules. So routes define path for packets, leaving instances, and firewall rules control traffic among VM instances. Then all of these machines at some point need to talk to the internet. Now, typically, if you have a public IP, you can directly go to the internet, but which is normally not allowed. So you use VPC routing to actually connect to the internet or outside the network. Then comes down to that you could have a similar network, another network, VPC2, and you might have to interact with that another VPC. Now that's taken care by the network peering. So VPC networks can be connected to other networks in different projects. So this could be in a different project or altogether are different organizations. Peered networks remain administratively separate. Routes, firewalls, VPN, and other traffic management tools are administered and applied separately in each one of the VPC networks. Now let's look at VPC peering a little bit in detail. So VPC peering enables you to connect VPC networks so that the workloads in different VPC network can communicate internally. And it's really important because as a big organization, you're always going to have multiple projects running. You're always going to have different departments. You're always going to have different people working on different systems. And most often there comes a need where you need to talk to another system. Now, how can you do that connection securely without exposing your public IPs or without even having public IPs? So VPC peering is a very good option for that. Reason why? Because traffic stays within Google's network and it does not traverse the public internet if these two different networks are peered together. If you have multiple network administrative domains within your organization, like different department, etc., it allows you to make services available across VPC networks by using internal IP addresses. If you offer services to even other organizations, it allows you to make those services available by using internal IP addresses to those organizations. So think of a company where you interact with a lot of your partners. Then you can use VPC peering to connect to peer with their VPC so that the communication can happen internally and that to end within Google's network. Now, if you look at this example, there's 3 projects, project 1, project 3, project 2, and project 3. Now, each one of these networks, they can be peered together. So you can peer project 1 and project 2. Each and every VM and instances, they can communicate using internal IPs. And the traffic will stay within Google's network. The same goes for something which is outside Google. So connection to on-premises network, because there's always a lot of concern in terms of security connecting from cloud to on-premises networks. So VPC peering is very handy and it's very useful. Let's look at some of its main features. So it allows internal IP address connectivity across two VPCs, regardless of whether they belong to the same project or the same organization. Traffic stays within Google's network, which is very important, and it does not traverse the public internet. Then it works with it works with Compute Engines, GKE, and App Engine flexible environment. Peered VPC networks remain administratively separate, so routes, firewalls, VPNs, and other traffic management tools are administered and applied separately. So even if you are peering them, that doesn't overshadow the routes and firewalls and the VPN setting that's done for that project. So it's still maintained that. Only thing it allows is the communication between machines internally. Now that also, again, it will depend upon whether one particular machine here has firewall open for ingress. Now, where is this most useful is any SaaS based ecosystem. So any of the SaaS providers, for example, MongoDB or Confluent or any of the SaaS providers who supply their products on Google Marketplace. This is really useful for them. Organizations with several network administrative domains. So a lot of different departments within a company, a lot of different groups, a lot of different pillars, if they all need to interact with each other. In fact, a lot of different business units as well. Then the last one is that it gives you several advantages. So a lot of these things you can achieve by using an external IP addresses. Because once you have an external IP addresses, outside systems or any other system can access you, but the traffic will come through internet. So over using external IP addresses, it gives you a benefit in terms of network latency because it's faster, network security because the traffic stays within Google's own network, and the networking cost egress. Now with that, let's look at another aspect of creating VPCs. So if I just look at let's look at a problem statement, or when you are starting on a project, what are the requirements? So as part of one business unit, there's always multiple projects that's running. And most often, if each and every project is taking care of their VPN on their VPC and everything, so there's a lot of administrative burden on each and every squad. So what you would ideally want is an administration team, or let's say an administration project, to take care of all of the networking requirement, and the project only focuses on actually developing the application. Now within Google, there's a concept of shared VPC. So shared VPC allows an organization to connect resources from multiple projects to a common virtual private cloud network. So rather than each one of these projects creating their own network, you can create one network, and that can be shared across all projects, so that they can communicate with each other securely and efficiently using internal IPs from that network. So now the host project, they they have the shared VPC network, which is again they take care of the region and the subnetting part of it. And then you have service projects who use the shared VPC network, and all they do is basically spin up their instances and get on with their job of developing applications, and they can communicate with the instances from the shared VPC network. Now, to in terms of the definition, the host project is it's basically the project which has that shared network, and the service projects are the ones which are attached to the host project. If we look at it from a different angle, the biggest problem, the biggest thing that it tries to solve is the security best practice. The shared VPC admins can delegate the networking and routing, access control, and all kind of requirements to a network admin or a security admin. The service project admins don't have to worry about it. So this is kind of, it's like a centralizing the networking and security aspects and abstracting it away from application development teams. It also applies and enforces consistent access control policy at the network for for multiple service projects, and that's typically the case nowadays. Is different teams going through, imagine different teams trying to build something, and they all have to take care of their networking as well as going through security clearance and all of that. So this is a very good way to centralize or abstract away all of the networking and security requirements for especially for a very distributed ecosystem. You can also think of it this way, is that you can use service projects to do the separate budgeting or internal cost center. So the return on investment will become much easier to manage with the concept of service projects. So going back to our requirement is that speed to delivery in terms of application development can be achieved faster with the approach of shared VPC. Now let's look at load balancers. Load balancers distribute user traffic across multiple instances of your applications. By spreading the load balancing reduces the risk that your application experiences performance issues. It's a fully distributed software defined managed services, which is very important to call out. It's a software defined managed service which distributes user traffic across multiple instances. So if you take this example, is you have different requests coming from different kind of devices from different locations, and your application is sitting on some backends, which is a compute engine and a cloud storage. Now that's where cloud load balancing plays a role. It receives the traffic from all of the resources and it distributes it to your backends. Now it does it in such a way and that you're depending upon the request, your backends can scale automatically. Now let's look at some of its features. It provides a single IP address to serve as the front end. So you don't have to worry about how many servers are running in the backend, what are different kind of services running in the backend. It provides you a single IP address to interface all of the request. There's an automatic intelligent auto scaling of the backend. So depending upon the request, it intelligently auto scales the backend. Layer 4 based load balancing to direct traffic based on data from network and transport layer protocols such as IP address and TCP or UDP port. So it takes care of layer 4 based. So it's basically based on IPs and based on ports and all of that. Layer 7 based load balancing to add content based routing decision based on attributes such as HTTP header and the uniform resource identifier. So it's basically based on /purchase, /payment, /search. So those kind of content based routing, it can do that. And another the next important bit is it integrates with cloud CDN for cached content delivery. So think of the point of presence or the edge locations where it you depend on a lot of caching, and to make any application global you depend on a lot of caching of the data across the globe. So it does support that as well. So rather than request being sent all the way to backends, it uses its cache to respond to the requests. Now, load balancing is typically two kinds: external load balancing and internal load balancing. External load balancers, they distribute traffic coming from the internet to your Google Cloud's VPC networks. It requires that you use the premium tier of networking service tiers. For regional load balancing, you can use a standard tier. While on the other side, internal load balancers distribute traffic to instances inside of Google Cloud. So with that, let's dig a little bit deeper into external versus internal load balancing. So the following diagram illustrates a common use case, which is how to use external versus internal. So in the illustration, traffic is distributed like this. So the traffic from users in San Francisco, Iowa, and Singapore is directed to an external load balancing, which is on this port. The external load balancer distributes that traffic to different regions in Google Cloud Network. So it goes to US Central 1, it goes to US Central 1B, and it goes to Asia East 1A. Now, after the traffic is inside Google's network, two internal load balancers. So you can see it here and here. Each distribute traffic within their respective regions. So within US Central 1A and within Asia East 1A, these interload balancers distribute the traffic. Within US Central 1, internal load balancer distributes traffic between two zones, US Central 1A and US Central 1B, which is the top, this top green one, and the middle green one. Within Asia East 1, internal load balancer distributes traffic within one zone. So apart from where the request comes from and where the request needs to go, and whether it needs to be handled externally or internally, there are some more consideration in terms of the traffic types. So for HTTP and HTTPS based traffic, you use again external HTTPS load balancing or internal HTTPS load balancing. For TCP related, you use TCP proxy load balancing or network load balancing or internal TCP UP load balancing. Similarly, same goes for UDP traffic. So next up we will look at is how do you choose between external versus internal, and then how do you choose between HTTPS versus TCP versus UDP versus the network load balancers. So let's just start with the request coming from outside GCP. So you have either IPv6 client or IPv4 client. They are external request. The request is coming from internet to GCP. Now when the traffic comes, it's either HTTPS traffic or HTTP traffic or TCP traffic or UDP traffic or external network load balancing, which means regional, or it's a regional traffic. Now, if it's an HTTPS traffic, you can use HTTPS load balancing, which is based on the URL map, it routes the traffic. HTTPS load balancers normally use forwarding rule. They support SSL certificates, and it's the layer 7 of OSI model, and it does support IPv4 as well as IPv6. Now, if it's a TCP traffic, then you look at whether the SSL needs to be offloaded. If the SSL needs to be offloaded, then you use SSL proxy. So SSL proxy, first thing, it's a non-HTTPS traffic. SSL TLS traffic terminates at load balancer. So if you have a requirement of SSL being offloaded at the load balancer, then you will use SSL proxy. It provides certificate management, internal intelligent routing, again SSL policies, and it does support IPv4 and IPv6. Now, what if you don't need to offload SSL? Then the next decision criteria is whether it's a global load balancer or IPv6. If yes, then you use TCP proxy. So if you're following it, it's a non-HTTPS load balancer. You don't need to offload SSL. So it's a single IP address, basically for all users, non-HTTPS and non-SSL, terminates TCP session at the load balancer layer, and it does have IPv4 and v6 support. Now, what if it's not? Then you need to preserve client IPs. So in that case, if you need to preserve client IPs, if you don't need to preserve it, you will use TCP proxy. If you have to preserve it, you will use external network load balancing, which is the regional load balancer. It also is called external TCP UDP network load balancing. It's a regional pass-through load balancer. A network load balancer distributes external traffic among virtual machine instances in the same region. So so this one is applicable only if it's in the same region. You can configure a network or the regional load balancer for TCP, UDP, ESP, and ICMP kind of traffic. Now, if it is a UDP traffic, straight away you will use the regional load balancer, which is the external network load balancing. If it is an external node regional traffic, you will use the regional load balancing. Now, this was something which was coming to Google from outside. What about the traffic which is from internal? And internal, it only supports IPv4. So internal traffic to or from internal IP addresses. Then it's either TCP traffic, UDP traffic, or HTTPS traffic. If it is a TCP traffic or UDP traffic, you will use internal TCP UDP load balancer, which again only uses internal IP addresses. It supports regional managed instance groups. It's built on Andromeda network virtualization stack. Load balances TCP UDP traffic behind an internal load balancing IP address. Same concept of external load balancer, but for internal. Then if it's HTTPS traffic internal, you will use the internal HTTPS load balancing. So the intention of this slide was that load balancing is a very important capability for, in fact, most of the application, most of the highly scalable distributed application, most of the web applications. It's a very important concept. Now, how the load balancers work, especially through layer 4 request, and then the pass-through request routing based on layer 7. There are different ways to select different load balancers. A lot of times as part of your applications, you also have to utilize some ingress controllers. So it's very important to get a good understanding of how these load balancers differ within themselves. As a face value, even if you don't remember or understand each and every different kind, just remember the pattern, how the request comes in, and what are the obvious choices, especially for HTTPS ones, regional ones, TCP as well. As long as there's you need to offload SSL, or internal ones, it's pretty straightforward. So I hope this was useful. Thank you.